All right, this ditto is an introduction to same base problems. However, you've been doing same base problems for years now, integrated 1 and integrated 2. It's just these might get a little bit harder with some skills that might be a little bit different than you've been taught. The first few problems here are very straightforward. I know we do these right in integrated 1. So let me just fast forward a little bit so you don't have to watch a ton of video here on some of the tougher ones on this worksheet. I'll start with number 5 here just because these numbers are kind of crazy, 32 and 16. But I'm hoping by now you recognize that the base of both of those numbers would be changed to are 2's. So 32, for example, is going to be swapped out with 2 to the 5th power. And the number 16 is going to be swapped out with 2 to the 4th power. And when there's other junk around it, we better use parentheses and bring that exponent down. That exponent there says 2x minus 1, which is kind of hard to read. So I'll bring that down because you have to remember that when you have an exponent that we just created and it's raised to another exponent that was already there, that you have to multiply those exponents. In this case, we have to distribute those guys there. So this 2 to the 5th power, just going to bring it down. This 2, bring it down, but 4 times 2x and the 4 times the 1 would give me 8x minus 4. If we distribute, now I don't have those parentheses anymore. Once the bases are the same, you can ignore them. Okay, we did our job of making them the same. Now we just got to make the exponents the same. So we set the exponents parts there equal to each other, and we just solve that algebraic equation. Very common to have a fractional answer, so don't panic when this happens. Let's see, we get 9 is equal to 8x, so x is 9/8. Very common to have an ugly fractional answer. Okay, then we had some fractions. So for example, here's the 32 and 16, just like it was here. So both those numbers, I'm going to swap out again. Here's 2 to the 5th power. 16 is 2 to the 4th power. And it's very similar to the previous problem. Nothing has changed except what I have to do next. I have to move this guy to the numerator. And if you remember, when you move a number that has an exponent from either the denominator to the numerator or vice versa, all you have to do is change the sign of the exponent. So that is what happened to that 5. I got to distribute over here just like we did on the previous problem. And now the bases are the same. I'll set the exponents equal to each other and solve. -5 equals 8x minus 4. 8x equals -1. So -1/8 is our answer to that guy. Okay, this next row introduces the same kind of theme here where you've got to recognize this skill. Here the bases are the same. And we have to ask ourselves, well, what are we supposed to do with the exponents when the bases are the same and they're being multiplied together? And to jog your memory, what if I threw over here x to the 3rd times x to the 4th? Do you remember what to do with those? Yeah, it's add x to the 7th. So these guys can be added. We can write one base. The 2 just becomes a single base as long as we add those exponents together. Now, they're not like terms like the 3 and the 4 were. So I just keep them separated with a plus sign. The number 32, let's go ahead and swap that out with 2 to the 5th power. Now, here's what's a common step just to save some space. I got to put 2 to the 5th power, put that in parentheses, and bring down this x minus 3. Or I can anticipate that I'm about to write a 5 right here and distribute the 5 just to save a step, save some space. So that would give me 5x minus 15. I hope that didn't go too fast. Like I said, I swapped 32 out with 2 to the 5th power, and the 5th power has to be distributed just to save a step. Once the bases are the same, you can ignore them. Set the remaining exponents equal to one another to find out when they're the same. Subtract 2x from both sides, add 15 to both sides, and then finally divide. Looks like 6. Okay, so these are all the same type of problem there. Let's jump down to this one. Maybe it just looks a little yuckier. Number 10 here. So I see 4, 32, 8, and 16. Those are all going to be bases of 2's. So 4 I'm going to swap out with 2 squared. And I wrote it off to the side because I'm going to expect some of you to go, okay, that's 2 squared, and then I have to move that to the top, and it's going to become 2 to the negative 2 power. And just go from here to here and actually not actually write that step. Same thing here. 32 is 2 to the 5th power. And the 5th power that I just said has to be distributed to that x minus 1. I hope it's x minus 1. Giving me 5x minus 5. My vision's going bad. Over here, the number 8 is 2 to the 3rd. The 3rd has to be distributed to that x plus 2, giving me 3x plus 6. And lastly, the number 16 is 2 to the 4th power. So there's a step right here that I'm probably going to avoid just to save some space. Right now, these bases are the same, so I'm supposed to add these exponents to each other. Now, I could put a plus sign here and add those two together. I could add the like terms together, or I'm just going to write the exponents with a plus sign in between them and not even write the 2's anymore. See, those 2's became a single 2, but I don't want to write that single 2 right here because in the next step it would be gone anyways. 3x plus 6 plus 4 is a very common place where people would put plus 10, and I totally could have put plus 10. I just don't. I don't know why. I think it has to do with the fraction busters that are coming later. So these two exponents get added together. These two exponents get added together to form a single base of 2, and then I would drop the 2's. So I've already dropped the 2's at this point to save some step because this ditto is very squishy. So I can solve this equation not too bad. Bring this 3x over here. That's going to give me 2x. At the same time, this is negative 7, so I'm going to add 7. That was 10 we said earlier, so 17. So it looks like we're going to get 17 divided by 2. Keeping that as a fraction since the directions say no decimals. Okay, so let's dive into a radical symbol, a square root symbol, and see if we remember how to get rid of that. First of all, 27 and 9, going to swap those out with 3's, right? 27 is 3 to the 3rd power, so the 3rd power and the x turn into 3x. And before I get rid of that radical symbol, I'm going to swap out a 9 with a 3 squared. And now the part I hope you remember, to get rid of a square root symbol, we write the exponent as a fraction. This is the root. It's the root of the problem, and the root of the problem goes underneath the fraction bar. So that 3 went there. This 2 went up there. Okay, so it's this exponent on top of the root here. Once you get the bases the same, set the exponents equal to each other, and then solve. Now, right now I should divide both sides by 3, but 2/3 divided by 3 there is an illegal answer. You wouldn't want to leave 2/3 divided by 3. I'll show you something on your calculator in case you ever needed to know this. 2/3, so 2 divided by 3, which I hit, you'll know is that cruddy decimal, and then we would divide that by 3. 2/3 divided by 3 is this decimal, but we're supposed to stay away from decimals. So if you have a graphing calculator, it's got a cool feature. By hitting the button that says math, right underneath my green button, math, number 1 there is convert to a fraction. So if I hit enter right now, since that was the first option, it's going to take the previous answer and convert it to a fraction. So I can type 2/9. Okay, 2/9 is my answer here. Converting to a fraction is a cool feature to know on a graphing calculator if you didn't know that already. All right, that video is 9 minutes. I'm going to stop right there. I'm going to keep going on the second video and do a few of these last 3, these tough ones, okay? See you in a second.